Hello everyone, and welcome to this fourth video dedicated to the FCC reaction section. In the first three parts, we described the different process sections, the feed characteristics, and the injection of the feed into the reactor. Before going further, let's have a look on the catalyst. This catalyst is in the form of a powder. It consists in very small spheres whose diameter varies between 20 and 100 microns, with an average value around 60 to 70 microns. For information, the diameter of these spheres is comparable to the particle diameter of a wheat flour. These catalyst particles present a rather complex chemical structure. This catalyst is essentially composed of silica, approximately 70% by weight, and alumina for approximately 25%. So, to be simple, the catalyst mainly consists in silicon, aluminium, and oxygen. Rare earths are also added on the catalyst to improve its thermal stability. On top of this main cracking catalyst, additional catalysts are often added. For example, catalysts to increase the yield of propylene are added. This allows to increase the economical profitability of the unit. DeSOx catalysts are also considered to capture SOx. This catalyst prevents SOx to be found in a regenerator flue gas. For memory, these flue gas are released to the atmosphere, so DeSOx catalyst reduced the SOx emissions. We will see later in the process that this catalyst is recycled. Indeed, the catalyst deactivates very quickly during the reactions when it is in contact with the VGO feed. It must then be regenerated to restore its activity. There is therefore a difference between the catalyst that is daily added to compensate for the natural losses of catalyst and the so-called equilibrium catalyst, which is representative of the overall inventory in the process. The equilibrium catalyst has been in contact with the liquid feed several times during its lifetime. That's why the catalyst presents a concentration in nickel and vanadium which is much higher than in the fresh catalyst. Indeed, these two metals are deposited on the catalyst surface and have a strong tendency to reduce its activity. These effects will be compensated by adding fresh catalyst and purging equilibrium catalyst. But by the way, what are the chemical reactions that will occur in the reactor? We recall that the VGO feedstock has been preheated to 220 degrees C. Then the VGO has been introduced into the reactor in the presence of atomization steam and with 750 tons per hour of very hot catalyst, at around 700 degrees C. When the feed meets the very hot catalyst, this VGO completely vaporizes and undergoes a series of chemical reactions. Indeed, it will crack in a multitude of molecules that are much lighter than the VGO. Indeed, the VGO has a molecular weight between 400 and 450 grams per mole. The mixture of molecules resulting from the cracking of the VGO will be about 100. With such a drastically molecular weight reduction of the gaseous mixture, the cracked VGO takes much more volume and is accelerated in a so-called riser equipment. The mixture of molecules and catalyst therefore follows an upward movement in the riser. As a reminder, the VGO consists of paraffins, naphthenes, and aromatics, with a high number of carbon atoms, ranging between 20 and 50. Remember, the straight-run VGO does not contain olefins. Thus, no carbon-carbon double bond. Here is a simplified review of the various reactions that take place in the reactor. First of all, long paraffins will tend to crack in two lighter molecules. This results in the formation of a paraffin and a branched olefin. This reaction requires the breaking of a carbon-carbon bond, and the operating conditions as well as the nature of the catalyst promote a break in the middle of the hydrocarbon chain. So we have no formation of methane. The branched naphthalene will also crack at the ring location. This results in the formation of paraffins and olefins. We will also have the formation of aromatic molecules. The naphtheno-aromatic molecules will undergo an opening of the naphthalenic ring and a breakdown of the side chains along the aromatic ring. This will lead to the formation of paraffins, olefins, and aromatics. Finally, the polyaromatic molecules are very little prone to crack and will form coke. This coke will deposit on the surface of the catalyst. So, if we take a step back, we see that the feed containing mostly paraffins, naphthenes, and aromatics will crack in shorter paraffins, olefins, and aromatics. As far as the polyaromatic molecules are concerned, they will remain on the catalyst in the form of coke. This will explain the high levels of aromatics and olefins in FCC products. Once we have seen the main chemical reactions, the question you may now ask yourself is, okay, cracking molecules produces light molecules. But what is the selectivity of the catalyst? Or, in other words, how are these cracked molecules distributed? To answer this question, we need to introduce the notion of yield. Well, that's it for the fourth part. See you very soon for the fifth part. In the meantime, do not hesitate to test your knowledge by doing the quiz, whose link is available in the description of the video. Do not also hesitate to subscribe to my YouTube channel. Refining is exciting. See you very soon for the fifth part. Bye bye!